and Professor Zehra is in Sabancı University, and she's a co-chair of the Scientific Advisory Committee, the SESAME, and teaching biophysics. He will present us the first talk about synchrotron light source in the Middle East, Germany. Please.
Thank you. So this was a very kind introduction in English, which meant that I can continue sort of smoothly in English. Otherwise I was going to say with my broken French, apologize for not talking in French. I'm going to tell you about something quite unusual that is happening in the Middle East at the moment, and that is the SESAME project. And SESAME project has been around for some time. It's a project that is established under the auspices of UNESCO many years ago, and I'm going to give you a brief history of SESAME also. But I just wanted to say, maybe, can you help me? Can you bring this here so it's easier for me to change the slides? I guess you all know about Ali Baba and the robbers, the party robbers, and talking about open sesame, open. So SESAME actually in this case stands for Synchrotron Light for Experimental Science and Applications in the Middle East, and it's a third generation synchrotron radiation source. I think you probably heard about what the synchrotron radiation source is. I will tell you more about that when I tell you about my work tomorrow. But synchrotron radiation sources are facilities where we get very high intensity radiation. It's a photon source. And this is a third generation, meaning that it's not only a storage ring. Again, I will give you a bit more detail tomorrow, but it's not only a storage ring, but it also has insertion devices in the storage ring. It's to increase the intensity and to allow to work in a wider energy range. So this is a facility that is being established near Amman in Elan, and it's actually already there. Now it's quite interesting. I don't know how much you know about synchrotron radiation sources, but there are more than 60 synchrotron radiation sources in the world, but there are none in the Middle East. Now this means something. Why is there none in the Middle East, and why is there so many other, synchrotron radiation sources around the world? Now there are so many around the world because these synchrotron radiation sources allow us to perform many different types of experiments in only one concentrated facility. And there are none in the Middle East. I don't know exactly why, but maybe partly because it requires rather advanced technology to establish one of these light sources. And we are trying to go against this trend at the moment by establishing this facility in the Middle East. Now, that's one unusual feature of SESAME, that it's a synchrotron light source in the Middle East. Another unusual feature about SESAME is its members. The members are, as you see there, not the usual people, not the usual states that you would see sitting around the table at the same time. Such as you don't get Israel and Iran sitting around the table at the same time. But these are actually Israeli and Iranian officials in the context of SESAME sitting together around the table. So there is Bahrain, Cyprus and Turkey are another two countries that don't always sit around the table together. And so on. We can actually go on this list. I don't know who usually sits together around the table in this list in a normal day or on a normal dinner table. Let's put it that way. Okay, so but these countries have actually gotten together to establish this this laboratory, and there are some observers that are giving support to this facility, and those observers include France, Switzerland, Italy, Japan, Germany, USA, Sweden, etc. Now, you may wonder then, what is going on when you get these unusual, as they say, bedfellows together? What is the actual objectives? Now, the actual objective is actually science, because SESAME is set up by scientists. You will see in the coming slides that some scientists actually initiated this program. So it's set up by scientists, and it strives to establish an excellent laboratory in the Middle East. This is very important, because if the science is not good, SESAME will not work. It doesn't matter what other objectives it has, it will not work. So the first objective is to foster excellence in science and technology in the Middle East. Another objective is actually by establishing such a facility in the Middle East, we hope that it will help to reverse brain drain and bring some scientists that are actually working abroad to the region. Thirdly, I said these facilities are high technology facilities. That means that you actually have to develop that technology in the area. So in that sense, it's very important for establishing the technological infrastructure in the area. And of course, we aim to increase understanding among people in the region through the language of science, because science is a language where other factors do not interfere. Scientists are curious. They like to talk to each other. They like to find out what the other guy does. Therefore, they can talk to each other. It doesn't matter which country, which origin, or which political background they come from, they can talk to each other about their projects. And once they start talking to each other about projects, they get to know each other. They learn to trust each other. And this, we hope, will help to improve the understanding of people in the region. Now, as I said, SESAME has been around for quite some time. It was conceived as an idea of scientific cooperation in the Middle East after the experiment of CERN. I guess you all have heard about CERN. CERN is the high energy physics laboratory that is in Switzerland. And it was established actually after the Second World War, when scientists sort of pulled themselves together after the war. They thought it would be very good to have a scientific laboratory where French, German, and British scientists work together and Italian scientists work together. And that's how CERN was established. And so those people moving on from CERN and seeing that CERN has worked, have thought that maybe we can do a similar experiment in the Middle East based on experience gained from CERN. So they came together and they actually initiated some efforts in UNESCO. And in the meantime, there was a synchrotron that was being dismantled in Germany, BESSI in Berlin. And so they thought it would be a good idea, maybe some parts of BESSI 1 can be donated to this facility that was going to be established in the Middle East, and somehow provide a center around which this facility could be built. And interestingly, the SESAME Council directors, chairs, have been ex-directors of CERN. So the first chair of SESAME Council was Herwig Schopper, who was a director of CERN, and then followed by Chris Llewellyn-Smith, who is the current chair of the council, and he was actually the director of CERN when the LHC project got going. So then, around 2002, SESAME was launched officially it was approved by the UNESCO Executive Board, and it was launched as an independent laboratory under the auspices of UNESCO. And just about that time, in the meantime, as these political efforts were going on to establish SESAME, scientists were working on the ring that was donated by Germans to see how that can be improved, because it was obvious that it needed upgrading. And so, in fact, what has happened is that they decided completely not to use the ring from BESI-1, but we are having a completely new storage ring at SESAME. But some of the parts are, from BESI-1 are being used. I will tell you in a minute. So anyway, in the meantime, as the political efforts were going on, people were also working on how the scientific program of this laboratory would be developed. And here in the next picture, actually you see the components of the BESI-1 going to Aqaba in the boat. And Gus Voss, who we lost at the beginning of October, is one of the people who were involved in putting the SESAME project together. So he's watching it in Hamburg to see as the boat sails through the Elbe. So in 2008, there was a building that was undertaken by the engineers by Jordanian engineers, and this was actually inaugurated. And this building was financed by King of Jordan. And so this was easy to build. And then in 2009, we had the test operation of BESI-1, the microtron. Again, you will see this in a minute. And we expect that the storage ring will be operational in 2015. Now, so here it is. SESAME is actually there. And this is the building, which was completed in 2008, and it was designed and constructed by the engineers from Al-Bakr University. And this is inside this building. So the lower floor of this building is the experimental hall. And you see the shielding wall on the right-hand side, and beyond that shielding wall is the experimental hall where the beam lines will be. So this is now how it looks from the top in the experimental hall. Later on, this will be all also covered. Now, this is the basic. This is the basic structure of the storage ring you see here. Here, this part is the BESI-1 microtron, which injects electrons into the booster ring. And from the booster ring, through this transmission line, the electrons are injected into the storage ring. And as I said, this is BESI-1 component. The booster ring is BESI-1 component, but the most important part, which is the storage ring, is completely new. And that's also delayed us a bit, because this is an expensive part to build, this storage ring. And only about a year ago, we had a grant from European Union in collaboration with CERN. We got this grant to work to order actually the magnets for this storage ring. So on this storage ring, you have the magnets, as you see here, like little boxes. And from these bending magnets, you can get synchrotron radiation emitted out of the shielding wall, which you see here. And those lines actually represent the beam lines where you can do experiments. You can select X-rays from synchrotron radiation, UV frequency or infrared, and you can do experiments with all those different energy photons. So in SESAME, we're going to have 400 milliamps current in this storage ring, the 2.5 GeV storage ring. There will be possibility of 25 beam lines, 13 bending magnet beam lines. Those are these magnets that you see here. And then there is possibility of having 17 insertion devices. That is what makes it the third generation, so we have the possibility of having 25 beam lines on the whole around this ring. Now, I wanted to show you a few pictures from what has come from Germany and what we have achieved so far. This is the microtron that came from BESI-1, so that is the electron source, actually the heart of the synchrotron. That came from BESI-1, and luckily the person who actually operated this in BESI-1 retired, and just as we were assembling this microtron in Amman, he came over and he helped to make this, he helped to put it together. And then the team that you see here are the team of engineers. These are the machine scientists that are working at SESAME, have actually obtained the electron beam coming out of the first part of the microtron in 2009. Now the booster the first ring is being assembled, and that will be functional in 2013, and you see it here again behind the shielding wall being put together. So what about science? What can we do on SESAME? What kind of experiments can we plan? And what kind of expertise do we need to have in-house, and also what kind of people do we expect to have there? So the first, what we call the phase 1 beam lines, we are aiming for about 7 beam lines, and they are infrared beam lines. This is going to be a completely new beam line that is being built from scratch. And then there is the small angle, wide angle X-ray scattering beam line. There is a material science beam line, and as you see here, these are all now going to be located around this this part of the ring. And then we're planning on a macromolecular crystallography, extreme UV beamline, and XRFs and XRS, X-ray fluorescence beamline. I think these are also mentioned in the next slide here. So those are going to be the beamlines that we are hoping that will be ready almost immediately as the machine starts to operate. The infrared beamline is completely new. It's designed by a SESAME scientist, and it's being now put together. And then there is a powder diffraction beamline that is partially coming from the Swiss light source, because they're changing their beamline, so we got some part of it to use on SESAME. And then there is a X-ray fluorescence beamline, which is based on a German beamline at ESRF. Now, the science program, then what about the science you can do with these beamlines, or on these beamlines? What are the possibilities for different areas of science? We can do structural biology, we can do basic sciences, atomic and molecular sciences. We have possibility of doing environmental science, material science, and of course archaeological or cultural heritage work can be done using these different beamlines that I mentioned. Now, another point that I would like to make is that there is, in one of the users meetings, I'm going to tell you what I mean by a users meeting, there was a request for having a medical application beamlines. So what all this tells us is that synchrotron radiation sources allow you to do science in different areas. You can address questions from different areas of science, from archaeology to medicine, from material science to environmental science, using different beamlines, different facilities that are on a synchrotron radiation source. So this is, again, it comes back to what I said earlier. People are curious about each other's work. If I'm sitting next to an archaeologist, I'm doing my experiment on biological samples, and next door somebody is working on archaeological samples, I'm bound to ask, hey, what are you doing? What are your samples like? What kind of information are you after? So this is, synchrotron radiation sources have a special social structure which allows, I think, helps people to communicate. Okay, so what kind of examples can I show for these different fields? For example, in the case of structural molecular biology, macromolecular crystallography, you can work on structure of molecules in such details, I don't have to tell you this, that you can work on development of drugs. Or, in another tangent to this, using an infrared beamline, you can actually look at structure of, or the components that you may find in liver sections. You're able to tell lipid areas from protein areas. You may be able to say what the lipid content is like, if it's more or less, and you can get clues about diseases. Another area which is mine, and I will be telling you more about this tomorrow, is again working on structural biology, structure of molecules that may bind metals. I'm interested in proteins that bind metals, and I'm interested in proteins that bind metals, proteins from wheat that bind metals, because this affects our diet, etc., and I will tell you more about that. Archaeology, what can we do in terms of cultural heritage? We can analyze materials non-invasively, so you can have pieces of archaeological findings which can be analyzed, and we can find out what kind of metals were there, what kind of dyes were used, what was the techniques they used to build this vase, to make this vase, for example, and then we can say, oh yes, that is actually, the vase was found in Egypt, but they used a technology that was developed in Syria at the time. So we can non-invasively analyze materials. Similarly, we can look onto paintings, and we can try to figure out if the painting is, if there is another painting behind that particular painting that you see in the front. This was recently a big news in the Art Museum in Chicago. They found out that one of the paintings actually had yet another, I think it was from Leonardo da Vinci, there was another painting behind it. Or similarly, there was a recently found Archimedes theorem, which happened to be behind a Quran. They found a Quran in Istanbul, and that was analyzed, and it turned out that underneath there was yet another writing, which was some theorem of Archimedes. So we can do a lot of work non-invasively using this synchrotron sources. Now we have plans for second phase beamlines, and those are more ambitious. This we intend to be able to make upgrades on the new storage ring, which will allow us to have coherent beam, and also we want to use a technology that is called top-up for refilling the beam into the storage ring and have more intense photons. Not only that, but also have a particular time structure which can allow us to do different time experiments. So these are experiments that that's this photon probe experiments, and imaging using coherent scattering. We can do higher resolution crystallography on large complexes of proteins. And we can also investigate materials under high pressure. So these are all plans for the second phase of what we want to do at SESAME. This kind of information, what is it good for? These are some examples from different laboratories that are, for example, the Spring 8 laboratory is a synchrotron source in Japan. And the kind of work you do there is not only basic science, but there's a lot of work you can do application-wise. And this is a project about catalyzers that you use in the car, exhausts in the car, that is, for example, supported by Toyota Corporation. This is development. They understand, they try to understand how these different catalysts are working and how new catalytic materials can be produced. Medical applications, as I said, can go as far as actually taking fine detail Röntgen pictures, if you want, and using coherent light, we will be able to get higher resolution and be able to work with thicker samples. Now, who are using SESAME, or what do I mean when I said users of SESAME? Now, SESAME's users are actually people from the region or from all over the world who have some connection to the region usually, and who are working on different synchrotron light sources around the world. We come from all over the place, and we label ourselves as users of SESAME, and we try to prepare projects which can be directly carried to SESAME when SESAME becomes operational. So we have people from Israel, from Iran, from Egypt, from Pakistan, from Turkey, from Palestinian Authority, and more, who are actually, he's from Cyprus. So we are actually working together in different areas to bring science to SESAME. Now, it was when I first heard about SESAME, they had some people. Well, there were two instances. In the first instance, they wanted to have SESAME in Turkey. So at the time I was working in Germany on a synchrotron in Hamburg. And they contacted me and they said, would you support, would you join us, the group of people who wanted to have SESAME in Turkey? And I refused. I didn't want to go to join them because I thought this would be a very expensive project for Turkey to carry on its own. And also, it would be difficult for political reasons to have it in Turkey. The second reason, though, that I didn't want to be involved in this project at the time was I thought this is going to be a second-hand synchrotron. It's going to be a second-class laboratory in the Middle East where nobody knows what to do with it. It's going to die. It's bound to die. It's not going to work. So two colleagues of mine actually convinced me, first that the storage ring will be new, so this is not a second-hand synchrotron, and secondly that there was a very intensive training program already started. So this is very important because we need people to use SESAME. There's no point in having the laboratory there if nobody's going to use it, or if nobody knows how to use it. So there is an intensive effort to train young people to work on SESAME. And SESAME has funds. So the reason why I'm saying this, more sort of taking time to tell you about this, is because SESAME has training funds that can be used. So funds for young people to go to different synchrotron radiations around the world, to get training, and then come and use their expertise in SESAME. So these are some examples from Turkey. I happen to know them because I'm Turkish, but there are several examples also from Iran, from Egypt, that people have gone and used SESAME's funds to get training, and now they're waiting to use SESAME. Now, so as far as training is concerned, we put in a lot of effort to train people, but there are also a lot of workshops to train groups of people in specialized areas. There were there were workshops on structural molecular biology, on crystallography, and there's also one that was held on material science. So these workshops train people in different fields. Now, what is important are these users meetings, and this has stopped in the 11th users meeting in 2012, and this year we're having the 12th now users meeting in Amman in November, around 20th of November. So these are meetings where community gets together, they talk to each other. That's the reason why I also found this meeting very interesting and very helpful. I see a lot of young people coming together, talking and learning new things. So it's important that people who have interests in similar areas come together and talk about things. And users meetings usually have a very nice atmosphere. Now, this is an example where I wanted to show that here people were trained and then they came back. You see these people with a star. They're the ones who had nothing to do with synchrotron radiation to start with. They were trained in the context of SESAME, then they came back and started working for SESAME, and that's very important. There are several light sources around the world. Now, I said to you there are funds at SESAME that you can use to go to different places. Here are some examples of light sources of synchrotron radiation facilities where one can go and get training and then use that training in the context of SESAME. So these are some examples. I think the next few slides are some examples. And this funding comes from mainly from the International Atomic Energy Authority. And they provide us with different projects through which we can fund trainees going to different synchrotron radiation sources. And these are the fellows that have made use of the IAEA fellowships over the years. Now, we also receive different types of support from different organizations around the world. We certainly receive a lot of support from synchrotron light sources around the world, including Diamond in the UK, MaxLab in Sweden, ESRF in France, Electron. So all these not only train our people, but also give us parts or help us build parts, help us learn how to build magnets, for example. And I guess the main one, CERN, is not written here. I forgot to put it. Also, organizations provide support and funds for us for different purposes. Now, this is more or less what I wanted to tell you. It looks all fine. We're all scientists. We want to do science and we want to develop our own projects and go somewhere with them. But in terms of SESAME, there are some unusual challenges. And those challenges start with the political and social stability in the region. That, I believe, is still a long way to come. There's not much we can do on that as scientists. We can be advocates, but we're not directly involved in that. But there are other things we can do. First of all, bringing science as a priority in our countries is very important, because in the Middle East, including Turkey, science is not a priority issue. Science is not something that all the politicians will talk about or will ever campaign about or emphasize. But we, starting with the scientists from grassroots, we can put pressure to the higher levels. I think science is important in many aspects of our daily life, and we have to know the importance of it.